I'm part of the hardware team, and I'm also in charge of the PSpice development.
Hey everyone, my name is Anthony Dochai. My major is computer engineering, and my role for this project was a software team as well as database development.
Hi everyone, my name is Jude Bato. I was also a computer engineer. I was also on the software team, and my main focus was Qt development.
Okay, so some project motivation for our project. So the big picture of our project was to generate electrical energy from applied mechanical stress through the use of piezoelectric technology. So we wanted to create a tile that when you applied mechanical stress, this mechanical stress would engender an electrical energy that could be used to power household commodities such as a light bulb. And in this project, we used mechanical stress to power a light bulb. We'll show you later on in our video. Some related work, so historical and current context. There exists a company in Britain called Pavagen. That's where we got our inspiration from. They're actually a company that converts footsteps into energy through the use of Pavagen tiles, and they use these tiles on sidewalks. So we don't want to use these tiles on sidewalks. We want to use these tiles on actual roads where cars can drive over them using their wheels. And Pavagen uses this energy to power applications such as Bluetooth beacons. We're not going to use it to power Bluetooth beacons. We wanted to power household commodities, so light bulbs. So some originality of our project, we're using wheels, not footsteps. So actual cars will be driving over these tiles, not pedestrians. And we want to incorporate this on a much larger scale, so roads, not sidewalks. And this energy can be used to reduce generation loads from power plants.
So a project description. So the summary is basically what Anthony said. It was a physical tile that takes mechanical energy and converts it to electrical voltage. So we do this using piezoelectric pads. We can take the pressure from the weight of a car and produce energy. We already have a really large automotive industry. And if we put these tiles on major roadways and highways, due to the amount of actual road traffic, we can produce quite a bit of electrical voltage. So the societal impact. So a system of these tiles installed can create a lot of power generation, and emissions would be reduced due to the fact that it's a renewable energy source. So we're not really adding any energy for the production, but we're still taking out of the system. So another societal impact would be the possibility of breakage. If drivers don't follow the speed limit, it could cause delays. Some global impacts include we're increasing the renewable power generation while reducing carbon emissions.
Okay, so our project selection, or our HP diagram, which is the analytical hierarchy process diagram. So our main goal was to build a harvesting tile, and to do that, we need to take into account many things. The first of many was the cost of manufacturing. So we had to take in the cost. If we went over the cost, we couldn't build a harvesting tile. We also had to take into account the hardware modules, the implementation using PSpice. We had to switch over to PSpice because of the remote learning. Software team developed the MySQL database using phpMyAdmin, where all these voltage sensor readings would be stored, as well as humidity and temperature sensor readings. And this would be directly connected to Jude's Qt, which is the user interface that would display these voltage readings. The hardware would be connected to the booster circuit, the step-up AC to DC inverter, and the software and the hardware would be connected to the physical tile.
Okay, so the system description. So if you look from the bottom up, it would start off with the tile's pressure plates, which would get put into a transformer, then an inverter, then a microcontroller. And in this case, we chose Arduino. That would be connected to the user interface, and they would constantly be giving and sharing data between one another. The client would access the system through the user interface and would gain whatever data it needs. Saying that the user interface would also be connected to two separate databases. One of these databases would hold all the voltages per second, and the second database, we set it up for a humidity and temperature sensor that we also implemented. This all led to one output that the client would see through the user interface.
So, as my peers explained, our project uses piezoelectric technology, DC to AC inverters, and a boost converter circuit. In order for our project to work, we needed to get the piezoelectric technology voltage to a higher voltage in order to get the transformer up and running. So, in turn, to turn on the household appliances. Uh, our piezoelectric parts only produced 1.2 volts to zero point 0.5 volts with a 0.08 amps. Um, in order to get a transformer working, it needed at least 6 to 7 volts with 1 amp in order to get it up and running. This in turn would obtain a gain of 35 or more in order to get the, the transformer up and running. And for our DC to AC inverter, we use a asynchronous oscillating inverter. This will allow for the voltage to always be on, no matter in what state it's in. For example, if one MOSFET is on, the other one would be off, and it would keep alternating on a microsecond basis, ensuring that that the voltage is always constant. Here is the equations that we did. For the boost converter, we had to figure out the duty cycle. The duty cycle that we came about to be is 0.97. And for the DC to AC inverter circuit, we obtained the values at the base of the emitter and the MOSFET. In order for this to work, we don't need those two parts to be saturated. If it causes any saturation, it'll cause a short, leading the components to burn out. Here's our rough hardware design. This is a rough sketch of our tile design. The team developed a tile with 2 layers. Layer 1 is shown in figure 1. The inner layer, this layer will be the exoskeleton, the housing unit for the components. It won't necessarily be used for anything but a holding unit. As you can see here, the red portion would be used as an additional maintenance window in case we need to take out the circuits or replace any of the piezoelectric parts. This is the second layer. This is where the circuits will be placed along with the piezoelectric components. The circuits would be placed in the middle so they don't have any obstructions to it. And the piezoelectric components will be placed on the 4 corners of the tile. That way, the mechanical pressure would be equally distributed along the tile. And here, we used the SketchUp program in order to design a very high detail schematic that shows what our end tile would look like. The tile will have a foam case design. It'll be able to hold the second part of the tile snug enough, but also not too snug that we won't be able to open it up to do some maintenance on it.
Since we are using piezoelectric pieces to harness mechanical energy, we have to make sure that we have enough voltage to power up the light bulb or light bulbs. The circuit shown will step up the output voltage from the input voltage using our boost converter. How it basically works is the inductor switches on and off using the IRF 150 MOSFET to slowly power the capacitor, thus stepping up the output voltage for the load, which would be the light bulbs. And as you can see from the graph on the next slide, there's an exponential step up from the initial voltage to the output voltage. And for our second circuit on the next slide, we needed to figure out how to get AC to convert DC into AC. So we built a CMOS inverter that consists of a PMOS and a CMOS in the P-Spice. So on the next slide, as you can see, the graph shown, you could see the input logic is high, therefore the output is low, and vice versa. If the input logic was low, the output would come out high, therefore proving that our circuit is converting DC into AC.
Okay, so for our software design, here we have our voltage sensor and Ethernet codes. I took the most important pieces of code from our voltage sensor code. For character server, right underneath the int offset is equal to 20. That is my IP address or the local IP address and initialize the database. So that's how all these sensor readings would connect to PHP-MyAdmin. It'd be through my router. And that's how it would continuously update on a per second basis. Right below that, you see the IP address, 192.168.1 and 3. That is not my local IP host. That is the IP address of the actual Arduino Ethernet shield. It has its own IP address, and that's how it communicates with the database. At the bottom, you can see that it sends to PHP-MyAdmin database with a delay of, I put it there, for example, 3 seconds at 3000 is 3 seconds, 1000 would be 1 second, and that's just the interval that it would update continuously on. And on the right side, we see that I have two sections at the PHP-MyAdmin. We have a temp humidity section, and then we have a voltage and the readings right down there. And then we have the timestamps as well as the 7.72 voltages, as you could see. Okay, so here are our temperature and humidity sensor codes. It's basically very redundant of the voltage sensor codes. We had to switch a lot of things because the temperature and humidity are obviously not the same as voltage, so we had to change up the code a lot. But it basically does the same thing. It goes to PHP-MyAdmin and it updates continuously on a per second basis. And on the bottom left, I have the XAMPP control panel. That is just the control panel of everything. Without that, Arduino cannot communicate with PHP-MyAdmin. And in the beginning of the semester, we were having a lot of problems initializing the XAMPP control panel, but we finally got it to work. And through the admin of the MySQL database, that brings up the PHP-MyAdmin and allows us to store the voltages over there. So you could see on the right side, we have humidity and temperature readings. Humidity of 50, temperature reading of 70. I think that's like room temperature, very close to room temperature. Good.
Okay, so I did the Qt, and this is just 3 snippets of the Qt code, along with how the UI will actually look. So it's a simple terminal with 4 buttons, one being connect, disconnect, settings, and clear. So the way that'll work is that when the user is connected the Arduino to their computer, they will run this terminal and they would click connect, and that will just continuously show voltages on a per second basis. So the snippets of code, the first snippet of code I have there is the main window. So this is a pointer, which the widget is a parent, and it'll point to various different codes to try and allocate different things. The second snippet would be the structure of settings. This gave the actual UI communication with Arduino, telling it various informations, whether being the rate at which it collects from the Arduino or to collect from the sensor itself. And the third snippet is the actual UI itself, how it looks. And this allowed for the widget, the terminal, to be expandable. So you can use tools or other various settings.
So this is our integration test for the AC to DC inverter circuit. We only had 3 iterations. The first one was to build the circuit. Upon building the circuit, after testing it, I saw that it failed. The reason for its failure is that the MOSFETs have burned out. And upon the discovery of this, I saw that the resistance and wiring of the circuit did not allow for the circuit to go in the flow of direction that we wanted to into the transformer. The second one, after doing some minor adjustments and calculations, I saw that it gave proper readings at the transformer, but it still would not power up the transformer and thus to light up the light bulb. So that failed as well. And then the third one, after doing some minor adjustments with the wiring and the resistors, making sure everything was neat, I saw that it did turn on the transformer and turn on the light bulb. So after doing all these tests, I realized that it's better to do everything neat and proper and clean instead of being able to do this thing over and over again.
This is our unit integration test for our P-Spice circuits. My first test was to find out that the elements we were using were properly valued to receive our expected results. And the second test was to test our boost converter circuit that I constructed. It failed. So the third test of the boost converter circuit worked, which is because I removed the 555 timer and MOSFET I originally had placed in my circuit and replaced it with an IRF 150 MOSFET. And as you could tell from the previous graph, that turned out successful. And my fourth test was to test the CMOS inverter, which I constructed using PMOS and NMOS, like I said. And as shown as the previous graph, that turned out successful as well.
Okay, so for corrective actions, software, these are some corrective actions based on the problems the software team encountered and how we fixed them. So for the first test, we named it the Ethernet Shield connection test number 1, and that automatically failed. The connection from Ethernet Shield to PHPMyAdmin via XAMPP server did not work. These voltage readings were not being inputted into the PHPMyAdmin. They were not being inputted on a per second basis as well. And the reason for this is MySQL only works on port 3306. That is the only port MySQL works on. So if it's being used by your laptop, it just that database will just not work. So after freeing up port 3306, the XAMPP connection worked and the database was established. As you could see on the second Ethernet Shield connection test, it was a success. The second problem we ran into was the voltage sensor code to the database. The sensor values weren't being picked up for some reason by the voltage sensor. And that was because it could not locate the Ethernet Shield localhost address. So I didn't know that the Ethernet Shield had its own IP address. I thought we just needed my router. I didn't think that we actually needed the Arduino's IP address. So after figuring out the Arduino's IP address, this worked and the voltage sensor readings were inputting on a per second basis to my database.
Here we did some corrective actions for the hardware. For the tile design, at first we wanted to create our tile design using AutoCAD, but since we all had very limited knowledge of AutoCAD, it failed, and we looked into other design programs to design our tile. Our second one, we did not get proper dimensions for our tile. As we said, we wanted to implement this on the road, so we did not have the proper dimensions for the tile, the thickness, the width, the height. And so we talked to our peers in civil engineering to get proper measurements and appropriate measurements for our tile. And then in our third one, like I said before in our previous slides, we used the SketchUp design program in order to get the tile built and have proper dimensions.
Okay, so our switch to remote learning. So the first problem that we encountered was the construction of the tile. So we had bought all the materials, but we were unable to complete the construction. So we created a PSpice and a 3D Revit to substitute. And then the next one was the connection of the GUI to MySQL. So we each perfected our own software. So I perfected my GUI, made it more user-friendly, and Anthony perfected my SQL by adding a temperature and humidity sensor into the database. And the third problem was connecting the GUI to the physical tile. So we ended up creating PSpice equivalents and perfected the GUI due to the fact that we couldn't add them together.
Probably only have 1 more minute, so just move a little bit faster.
All right, understood.
Okay, so future work and project completion. So our goal was to make a device that would turn mechanical energy into electrical energy produced by cars to light up homes and street lighting. Some technical challenges included learning 2 different softwares, Qt and MySQL for me and Anthony respectively. And what remains to be done is to build the tile and connect all the electrical components as well as softwares together. And before production of the final product, we should develop a PCB to replace circuits as well as perfect the connection between the UI and the database.
Here's just a quick rundown of our bill of materials. So before the pandemic started, the team and I went to Home Depot and bought basic supplies to our tile. After doing the total, it came out to 126 with 10 cents. We were under our budget of $200. So this would give us excuse me, $33.90 left. $73.90 left that we could use in our later budget if we wanted to continue with this project. Here are our videos, our software videos. That's voltage sensor. That's the Arduino board. And here's the code. And it's showing right here in the database the values of the voltages. And now here's the hardware code. This is our DC to AC inverter circuit, which in turn turning on the light bulb. Some codes, standards and constraints. So since our project is more to the public and more to the government and power plants, we had to go with the NFPA 70, which is a National Electric Code. This standard is for the safe installation of electrical wiring and equipment in the United States. This code makes distinctions between high and low voltages and may require a license. The other code that we had is NESC. This is a definitive safety standard for the national electrical grid and communication systems. In the future, when we want to connect these tiles to the power grid, this is the code that we have to follow. Standards, we had to establish proper code to track the DC voltage values of circuits, along with creating proper circuit to successfully light up household appliances. Some constraints included connecting user interface to MySQL databases, programming languages, and a Qt constraint.
So what we have here is our ethical issues side. So one of the most important aspects of our project was safety. We had to make sure to paramount the safety, health, and welfare of the public, which can be found in the IEEE codes of ethics. Since the tile will be on roads, the tile should be durable enough to withstand the different weights of vehicles and weather conditions, also being easy enough to remove for future improvements or repairs. Another important aspect is to make sure we know our own pros/cons and ins and outs of our own project. This is described as maintaining high standards of professional competence, conduct, and ethical price, which can also be found in the IEEE Code of Ethics. And thank you.
References.
This concludes our presentation, and if you have any questions now, feel free to ask.
Any questions and
Yes, thank you, everyone.
Thank you.
Any questions?
concerns, comments?
No, good presentation.
Okay, thank you.
Thank you.
Thank you.
Thank you.
I think they might be right in it. Thank you, Professor.
Okay. Okay. Sorry. So let's welcome to our next team. Next team, the title is Smart Eco Tea Kettle, an energy efficient and intuitive redesign of electrical tea kettle. Let's welcome Marvel, Charles, and Alec.